Thanks, Sharon. So I'm Eric. I'm a software engineer at Databricks, and I'll be telling you about transactional rights. So first, a little bit more about Databricks. We're the team that started the Spark project, which is now Apache Spark, at UC Berkeley in 2009. Our company mission is to make big data simple, and we're doing that through our product, which is a unified analytics platform. So this talk is going to be a deep dive on the challenges in writing a cloud storage system such as S3 with Spark. So I'm going to go into why transactional rights are important, cloud storage versus HDFS, and kind of how current solutions are tuned for HDFS and what we're doing about this. So to kind of understand why transactional rights are important, it's good to look at the requirements for the writers. So as you probably know, Spark is a unified analytics stack that supports many different types of workloads. One common end-to-end use case we've seen is chaining of Spark jobs. And so what this means is that the output of one Spark job is consumed by another. So some examples here are, let's say you have an ETL Spark job that runs regularly. You might have people doing analytics on the output of that job. In more kind of advanced data pipelines, you might have ETL jobs that feed into further downstream ETL jobs. And really the requirements for the rights of jobs comes from the readers of the outputs of those jobs. So just to make this really concrete, let's look at an example of a writer job. Here we're using spark.read.csv to read some CSV files from some source in S3. We apply some data frame aggregations, and then we're telling Spark to append that data to another destination in S3, this time in Parquet format. And on the reader side, let's say I'm doing some analytics on that output data. I just need to tell Spark to read that data. Again, I can apply some further transforms to slice and dice that data. And the main difference from the previous job is that instead of writing it to some other destination, I'm just going to call .show to show the results directly to the user. So with these chain jobs, one requirement from the reader side is that if an upstream job fails, it shouldn't corrupt that output data. So this might seem kind of obvious, but when your writer job fails, you want it to fail cleanly. You shouldn't leave like garbage files, corrupted files, or partially written data, which might be problematic to clean up. Another requirement is that maybe you have multiple concurrent readers, and you want to read while those previous ETL jobs are running. And another requirement is that, and this is one that happens mostly in the cloud, is that you want the data to actually show up. You don't want it to be missing rows or have Spark throw a file not found exception on you. So to kind of summarize these requirements, basically we see that writes should be committed transactionally by Spark. So your files should be written atomically, and from the reader side, you should see a consistent snapshot of the data. So how does Spark support this today? Well, Spark's commit protocol, which is a component inherited from Hadoop, ensures reliable output for jobs. And the default implementation is this Hadoop MapReduce commit protocol. And how it works is basically during the execution of a Spark job, the output files for the job are going to be staged into a temporary location. It's only when the job finishes and we decide, yes, we want to commit this data, that the data is actually moved to its final destination. And if the job fails, we can abort and we delete those temporary files. So to kind of view this in a kind of timeline format, here we have a Spark cluster with one driver and 4 executors. We see that once the driver kicks off a job, the tasks are going to run in parallel on the executors producing output data. And when all the tasks finish, then we can commit. And this is what's going to move those files, the outputs to their final destination. So let's look at how this would work on HDFS. So HDFS is the Hadoop distributed file system. It's highly available and durable. And one nice feature is that it supports fast atomic metadata operations. So files in HDFS can be moved very quickly. So we use that commit protocol I talked about before. The commit step is going to use a series of file moves on job commit. And since HDFS is so fast at moving files, this is going to be very close to transactional. So again, let's look at, does this meet requirements if we use that commit protocol in HDFS? And it turns out pretty much yes, because the commit step is so fast, it's very unlikely you're going to get partial results or see those results. And also because HDFS is strongly consistent, your data is definitely going to show up. Okay, so we know reliable output works on HDFS, but what about in the cloud setting? you have a couple options here. First, you could run an HDFS work on every node. So this is basically replicating your on-prem Spark deployment in the cloud. Or you could use cloud-native storage systems such as S3. So there's a challenge here in that systems like S3 are not really true file systems. The API they present is more like a key value or object store. So how's that going to work? Well, fortunately, it's really not hard to provide a file system API over object stores such as S3. For example, the S3A file system is commonly used as an adapter here. This lets traditional Hadoop applications or Spark continue to work over cloud storage. But you're using an adapter. So the question is, what are you giving up in terms of like transactionality or performance? So in this remainder of the talk, I'm going to try to argue why HDFS really has no place in the cloud. And when you're using these adapters, there are going to be some trade-offs with the Hadoop commit protocols. And finally, I'm going to talk about a new commit protocol we've built that provides transactional rights in Databricks. So let's compare HDFS and S3. When evaluating storage systems, there are a couple of the top things you want to compare are cost, SLA, and performance. So let's first look at cost. If you try to compare just the raw storage cost per month to store a terabyte, with HDFS, it's going to cost over $100, even use the Amazon instances that give you the densest storage. In S3, it's $23, depending on your what storage class you choose. Another thing is human cost. So if you run HDFS yourself, very likely you're going to have to pay a team of Hadoop engineers to maintain this thing, or you're going to pay for vendor support. On the other hand, S3 is a fully managed service. You're not going to pay anything. Another big thing is elasticity. So S3 is with S3, you pay as you go for storage and for the requests you send to S3. But this is not true for HDFS. In HDFS, you maintain a set of nodes. You have to keep those nodes online, or you're going to lose access to your data. So if you consider these factors, cloud storage is likely at least an order of magnitude cheaper. And SLA. So Amazon claims many nines of availability and durability, and this matches our experience. We've only seen S3 go down twice in the past 6 years, and we've never lost data. On the other hand, when we talk to our customers, some of them have Hadoop clusters, and the availability they see is usually 3 nines or less. Finally, performance. So HDFS offers higher raw read-write performance per node because you can get disk locality. On the other hand, S3 decouples compute from storage. So you can scale the performance to your needs. For metadata performance, S3 is slower for listing files. So there are some workarounds here. You can just avoid listing files as much. And in Spark 2.1, there's more scalable partition handling support. But the major downside of S3 actually is that file moves require copies. And this is incredibly expensive. So overall, we see that cloud storage is preferred. Cloud-native storage is going to win in cost and SLA. You get a better price-performance ratio, and it's going to be more reliable. However, it's going to bring these challenges for ETL, mostly around the transactional write requirement. And there's a question that comes up of what is the right committed protocol for S3? So I went over the HDFS and S3 comparison quite fast, but if you're interested in the details, there's a blog post on the Databricks blog. Okay, so clearly the commit protocols are important, and it's a problem that's been thought about before. So let's evaluate some of the commit protocols in use today. So first, there's the Hadoop MapReduce commit protocol v1, which is what I described previously. And there's also a v2 commit protocol. So those of you that know more about this might also have seen something before called the direct output committer. And this is a commit protocol that basically did very little and was unsafe. And at this point, it's been deprecated and removed from Spark. So let's just look at the first two commit protocols used today. Which one is going to be better for the cloud setting? And to compare these commit protocols, we're going to look at performance, how fast is this protocol at committing files, and we're going to look at transactionality. So will a job cause partial or corrupt results to be visible to readers? So for the performance test, I'm going to use this synthetic benchmark. First, I call spark.range to produce some rows. I'm going to repartition those rows into 100 different tasks. and then tell Spark to append them to S3. So this is going to write 100 files to S3. And I'm going to run this job using V1 and then V2 of the Hadoop commit protocol. So here's the result. V1 takes over 100 seconds, and V2 takes around 20. So why is there this huge performance difference? Well, let's look at the timeline of the V1 commit protocol. So this isn't to scale, but you see that once the job finishes, there's this very long commit phase, and it's really long because the commit protocol is moving all the output files serially, one at a time, to their final location. And as we saw before, moves in S3 are very slow. They require copying all the files. On the other hand, the V2 commit protocol is implemented by moving the files to their final locations as soon as the task complete. So the Spark executors are going to be moving those files in parallel, which amortizes the copying cost. So we saw that the V1 commit protocol is slow. This is because it's copying files serially on the driver. And the V2 commit protocol is almost 5 times faster in this benchmark. OK, let's look at transactionality now. So one example situation is what happens to the job if there's a bad task. For example, there's certain input files of my job that have bad records are always going to cause a task to crash. So this will cause the job to fail because Spark, no matter how many times Spark retries that task, is going to continue failing. So we want that job to fail cleanly with no output visible to readers. So let's do that evaluation again. So in this example, on the 123rd record of my job, I'm going to throw an exception. So that's always going to fail. And again, I'm telling Spark to try to write the data to S3 with algorithms 1, and then I'll try again with algorithm 2. So the question we asked this time is not performance, but did the failed job leave behind any partial results? So we see that the V1 of the commit protocol did not leave any results, but V2 left over 8,000 rows. So if you're running a complex data pipeline, this 8,000 row is duplicate data that you need to manually clean up before running the job again. So overall, we see that empirically, while V2 is faster, it also leaves behind partial results on job failures, breaking the transactionality requirements. So you might think, OK, there's this trade-off. If you use V1 for correctness, V2 for performance. But really, is V1 that transactional? So let's do another test. Here, I'm just writing a billion rows to S3. And at the same time, in a different process, some other user is going to try to read from that directory and just count the number of rows. So if V1 was transactional, we expect to either read 0 rows or all 1 billion rows. But if you try this, you'll actually see that while the job is running, you'll be able to read an intermediate number of rows, which is not great. So really, V1 is not transactional on cloud storage either. There's this very long commit phase that is problematic. Like the driver could fail during that phase, or other users could come in during that time and read partial results. On HDFS, this was really not a huge problem because the window of vulnerability was so much smaller. So the overall problem with these Hadoop commit protocols, especially V1, is that it was designed with the assumption that file moves are fast. And V2 was really a workaround for cloud storages, but sacrifices transactionally when there are job failures. However, this trade-off is not fundamental. The question is, how can we get both strong transactionality guarantees and the best performance? So let's look at what an ideal commit protocol would look like. The job runs, and once it finishes, the commit should be instantaneous. There shouldn't be file copies or moves or anything of that sort. So how can you achieve this? Well, we took a look at this at Databricks, and we came up with some pretty simple ideas on how to solve this. So the basic idea we have is, since in Spark, the output files, the file names are controlled by Spark. So when a user writes a file in a job, we're just going to embed a unique transaction ID in that file name. And we're just going to write that file directly to its final location, not to a staging area. And when the job commits, all we need to do is mark that transaction ID as committed in some metadata service. And there's another change that's required here. when a user is listing files, we just need to ignore the file if it has a transaction ID that's not committed. And this is all implemented in the DBIO component of Databricks, which is a layer between Spark and cloud storage. So we do that. We use the same performance benchmark we had before with V1 and V2, and we see that this commit protocol, as described, is much faster, which is kind of expected because you're not paying any copy overhead at all. Let's also do a kind of an analysis of how fault-tolerant this commit protocol is. So we're going to compare different types of faults. The most basic kind of fault is a task failure, which Spark will automatically retry that task. And basically, any sort of commit protocol handles this. There's also a job failure, which is the example I described before, where a persistently failing task causes a job to fail. And as we saw before, the V1 Hadoop commit protocol is able to handle the situation just fine. However, the V2 protocol cannot. Finally, there's the worst case situation, which is the driver failure. And this might occur because of hardware failure or maybe some other error. So neither V1 or V2 of the Hadoop commit protocol can handle this. However, the transactional DBIO commit protocol can. And if we repeat that concurrent read test, we'll see that DBIO actually does provide atomic commit. If you read from S3 concurrently with the write, you'll either see no result or the full result. And this is actually guaranteed. Even there are no race conditions for this one. So overall, we see that this new commit protocol provides high performance and strong correctness guarantees. There are other features that come with it. One is that it is now safe to enable Spark task speculation. So for those of you not familiar, task speculation is important for reducing the tail latency of Spark jobs in case there are stragglers. So before, this was not safe to enable on cloud storage because of some of the problems of commit. Another feature that we can use with DBIO is the ability to atomically add and remove sets of files. We're pretty excited about this because this lets us do certain optimizations, such as compacting a large number of small files into a couple larger files to optimize read performance. And we can do this in the background without interrupting any readers of that data. Finally, we're able to provide enhanced consistency in many cases. So you might be wondering if there's any catches here. Well, there were challenges during the implementation. The biggest challenge for us was how do we guarantee compatibility with external systems like Hive that are not going through the DBIO component in Databricks? Well, our solution is to relax some of the transactionality guarantees. So if you're reading from an external system, you're not going to get a fully transactional experience. We do provide a command such as vacuum in SQL that does let you clean the data up into a consistent snapshot for compatibility with these external systems. And in many cases, DBIO will also automatically vacuum in the background to give a pretty good user experience. Another challenge is how do we reliably track the transaction status of each transaction? Well, the solution here we had is a hybrid of metadata files kept alongside the data files and a service component that provides transactionality. And we like this design because it lets us provide high availability, but at the same time, we have room to add more data warehousing features in the future, such as more transactions. So let's talk about rollout. So I'm happy to say that this is enabled by default, starting with Spark 2.1 DB5 image in Databricks. We're currently still in the process of gradual rollout, but more than 100 customers are already using this transactional commit protocol. And we're pretty happy that we didn't have to do any manual data migration or interrupt any customer workloads in order to roll out this feature. So in summary, we see that cloud storage is much preferred over HDFS in the cloud setting. However, it really requires a different design for commit protocols. And we were able to come up with a new DBIO transactional commit protocol that does not compromise on any aspect. So if you're interested in more of the details, we also have another engineering blog post that you can find if you search for transactional writes on cloud storage. Thank you.
Thank you very much, Eric. Now we have 5 minutes for Q&A, so if you have questions, please stand to the mic here. Looks like we have first one.
So how does the vacuum job, how can the vacuum job distinguish files that have not been committed yet, but will be committed versus they're real garbage because the job crashed?
Could you repeat the last part?
So you can create temporary files, then the job crashes, and then those files are garbage and should be vacuumed, but you may also have files that are still in the process of being, that will be committed. So how can the vacuum job distinguish between these two?
Yeah, so that's a good question. So the question was, there's this vacuum command, but how does it distinguish between files that are from jobs that are, let's say, permanently failed, or jobs that are just running for, let's say, many days? And the answer here is that while a job is running, we report its status, and as long as the job reports the status in a timely manner, the vacuum command can avoid deleting those files.
Any other questions? Okay, then, well, thank you for coming. That concludes for this session. Thank you, Eric.